something's out there. Something massive, something cold, something so distant it takes 10,000 to 20,000 years to complete a single orbit around our sun. We haven't seen it. We can't photograph it. Yet the mathematical evidence suggests it's real, and it's 10 times more massive than Earth. This is Planet 9, a world that shouldn't exist according to everything we thought we knew about our solar system. But the math keeps pointing to the same conclusion. There's a giant lurking in the darkness beyond Neptune. In 2016, two astronomers at Caltech made an announcement that sent shockwaves through the scientific community. Konstantin Batygin and Mike Brown claimed they'd found evidence for a ninth planet, not through direct observation, but through pure mathematics and computer simulations. The prediction was bold. The implications were staggering. And the astronomical world split into believers and skeptics almost immediately. Here's what makes this different from every other "maybe there's something out there" claim. The evidence doesn't come from a single strange observation or a blurry photograph. It comes from watching how dozens of distant objects move, objects so far away they barely reflect any sunlight, objects that take thousands of years to complete their journeys around the sun. These frozen worlds are telling us something. Their orbits are aligned in ways that shouldn't be possible unless something massive is pulling on them. 6 of the most distant objects we've ever discovered all point in the same direction. They tilt downward from the plane of our solar system at nearly identical angles. The odds of this happening by random chance? About 1 in 500. Those aren't lottery odds. Those are "something's definitely going on here" odds. But let's back up. How do you lose a planet? The story begins much earlier than 2016. It starts over a century ago with an astronomer named Percival Lowell. In 1915, Lowell became convinced that something was disturbing the orbit of Uranus. He called this hypothetical object Planet X, where X stood for the unknown, not for the Roman numeral 10. Lowell died in 1916, never finding his mysterious planet. But his search continued at the observatory he founded in Flagstaff, Arizona. In 1930, a young astronomer named Clyde Tombaugh discovered Pluto. For decades, astronomers believed they'd found Lowell's Planet X. Pluto was celebrated as the 9th planet, the final member of our solar system family. Except there was a problem. Pluto was far too small to cause the gravitational effects Lowell had predicted. It turned out those perturbations to Uranus's orbit were measurement errors. They weren't real. The search for Planet X was based on a mistake. Pluto's story took another turn in 2006. The International Astronomical Union redefined what it means to be a planet. Pluto didn't make the cut. It became a dwarf planet instead, one of many similar objects in the Kuiper Belt. The man who provided much of the evidence leading to Pluto's demotion, Mike Brown. He even wrote a book titled "How I Killed Pluto and Why It Had It Coming." The irony that Brown might now discover a true 9th planet hasn't been lost on anyone. So if the old Planet X was a myth based on bad data, why should we believe in this new Planet 9? Because the evidence is completely different. This isn't about measurement errors or wishful thinking. It's about patterns that emerge when you look at the most distant objects in our solar system, objects that exist in a realm we barely understand. The outer solar system is strange. Beyond Neptune, at distances greater than 250 astronomical units, that's 250 times farther from the Sun than Earth, you enter a region where sunlight is so faint it's almost meaningless. Out here, objects move in slow motion, taking millennia to complete their orbits. We've discovered dozens of these extreme trans-Neptunian objects, and they're revealing something unexpected. In 2014, astronomers Scott Shepard and Chadwick Trujillo noticed something odd. A handful of these distant objects had orbits that clustered together. They weren't randomly scattered across the sky like you'd expect. They were grouped, almost shepherded, as if something massive was organizing them. Shepard and Trujillo suggested an unseen planet might be responsible, something several times larger than Earth and more than 200 times our planet's distance from the Sun. Badigian and Brown heard about this clustering and decided to investigate. What they found went far beyond the initial observations. When they ran computer simulations of the outer solar system, trying to recreate the orbits of these distant objects, they kept hitting the same conclusion. Without a massive planet out there, the simulations couldn't reproduce what we actually observe. But add a planet with specific characteristics, about 10 Earth masses in a highly elongated orbit, and suddenly everything clicked into place. The simulations matched reality. The alignment of these objects isn't subtle. 6 of them point in the same direction when they make their closest approach to the Sun. They're tilted at about 30 degrees downward from the plane where the other planets orbit. This kind of alignment doesn't happen naturally in a chaotic system. Something organized it. Something massive enough to gravitationally dominate a region of space larger than any known planet. There's more. Badigian and Brown's simulations predicted that a second group of objects should exist, forced into positions at right angles to Planet 9 and into orbits perpendicular to the solar system's plane. 5 known objects fit this prediction exactly. The math predicted they should be there before anyone found them. In April 2024, Badigian and Brown published new evidence. They focused on a different population of trans-Neptunian objects, ones with orbits that reach inside Neptune's orbit. These objects spread inward from Neptune in a pattern that matches Planet 9's predicted gravitational influence precisely. Without Planet 9 in the simulations, this pattern doesn't appear. With it, the match is almost perfect. The study was statistically significant at about a 5 sigma confidence level, which in scientific terms means the probability of this being a coincidence is vanishingly small. Mike Brown stated it plainly. I think it is very unlikely that Planet 9 does not exist. There are currently no other explanations for the effects that we see. If Planet 9 isn't real, astronomers would need 5 or 6 separate unknown explanations for all the oddities they're observing in the outer solar system. That's possible, but it violates a principle scientists hold dear. The simplest explanation that accounts for all the evidence is usually correct. But here's what makes this search so difficult. Planet 9, if it exists, is unimaginably far away. The most recent estimates place it around 290 astronomical units from the Sun on average. To put that in perspective, Neptune orbits at about 30 astronomical units. Pluto's average distance is around 40 astronomical units. Planet 9 is 7 to 10 times farther out than that. At such distances, sunlight is incredibly weak. The planet would reflect almost no visible light. It would be extraordinarily dim, with an apparent magnitude somewhere around 21 or 22. That's roughly 25,000 times fainter than the faintest stars you can see with your naked eye. Even with the world's most powerful telescopes, finding Planet 9 is like searching for a specific grain of sand on a beach at midnight. You know roughly which beach to search, but the grain could be anywhere along miles of coastline. Previous searches have eliminated about 78% of the possible sky positions. That sounds impressive until you realize 22% of an already enormous search area is still enormous. The planet moves slowly, incredibly slowly. At its estimated distance, it would take between 10,000 and 20,000 years to complete one orbit. In the time since humans built the pyramids, Planet 9 has moved only a fraction of its total path. This makes it harder to detect because astronomers typically find distant objects by watching them move against the background stars. If something barely moves over months or years of observation, it can easily be mistaken for a distant star or galaxy. There's another complication. The planet's orbit is highly elongated. Sometimes it might be relatively closer to the Sun, perhaps 200 to 300 astronomical units away. At other times, it could be 600 astronomical units out or even farther. According to Kepler's laws of planetary motion, objects move more slowly when they're farther from the Sun. Statistically, Planet 9 is more likely to be near the far end of its orbit right now, where it's moving slowest and is dimmest. That's the worst possible scenario for detection. Yet despite these challenges, astronomers are confident they'll find it soon. The reason for this confidence lies not in traditional telescopes, but in a revolutionary new observatory that's about to begin operations. The Vera C. Rubin Observatory in Chile represents a complete game-changer for astronomy. This facility, a joint project of the National Science Foundation and the Department of Energy, has been under construction for years. It's equipped with the largest digital camera ever built for astronomy, and it's designed to do something no other telescope can match. Starting in 2025, it will photograph nearly the entire southern sky every few nights, creating an ongoing movie of the cosmos. Mike Brown calls it the perfect tool for finding Planet 9. If you were to hand me a big wad of cash and say, go build a telescope to either find this Planet 9 or find the best evidence possible for Planet 9, I would probably go and build the Vera Rubin Observatory. The observatory will capture images of roughly 10 billion objects over the next decade. Computer systems will constantly compare new images to previous ones, flagging anything that changes or moves. If Planet 9 is in the southern sky, Rubin will almost certainly detect it. Scott Shepard estimates the observatory has a 70 to 80% chance of finding the planet if it's real. But what if it's not in the southern sky? What if it's in the northern hemisphere, outside Rubin's view? That's where other telescopes come in. The Subaru telescope in Hawaii, with its combination of large aperture and wide field of view, is conducting its own search. Two teams of astronomers, Badijan and Brown along with Trujillo and Shepard, are working together, expecting the combined search to take up to 5 years. 5 years might seem like a long time, but in astronomical terms, it's remarkably quick. We're talking about finding an object that's been hiding for 4.6 billion years, an object that's never been seen by human eyes, an object that challenges everything we thought we understood about how our solar system formed. Because that's the real question lurking behind all of this. If Planet 9 exists, how did it get there? A planet that massive, that far from the Sun, shouldn't exist according to standard models of planetary formation. The solar system's outer regions didn't have enough material to build something that large at such distances. So where did it come from? The answer might be even stranger than the planet itself. The leading theory suggests our solar system once had 5 giant planets, not 4. Jupiter, Saturn, Uranus, Neptune, and a 5th world roughly the size of Uranus or Neptune. During the chaotic early days of the solar system, these giants were packed much closer together than they are now. They orbited in a dense disk of planetesimals, the leftover building blocks from planetary formation. Then, over millions of years, gravitational interactions between the giant planets and these smaller objects caused the planets to migrate. Jupiter moved slightly inward. The others drifted outward. This migration wasn't smooth or gentle. It was violent, chaotic, a cosmic game of pinball played with planet-sized objects. At some point during this upheaval, the fifth giant planet got too close to Jupiter. Jupiter, the most massive planet in the solar system with more than twice the mass of all other planets combined, acted like a gravitational slingshot. It flung the fifth giant outward with tremendous force. Most computer simulations of this scenario show the ejected planet being thrown completely out of the solar system, lost forever to interstellar space. But in a small percentage of simulations, something different happens. The ejected planet doesn't quite reach escape velocity. Instead, it settles into a distant, highly elliptical orbit, exactly the kind of orbit predicted for Planet 9. This scenario is called the Nice model, named after the French city where it was developed. The Nice model has become widely accepted because it explains several puzzling features of the solar system. It accounts for the late heavy bombardment, a period roughly 4 billion years ago when the inner solar system was pummeled by asteroids and comets. It explains why Neptune's orbit is slightly eccentric. It clarifies the structure of the Kuiper belt. And now, it might explain Planet 9. The ejection hypothesis solves a fundamental problem. You can't build a planet as massive as Planet 9 at such extreme distances from the Sun. There simply wasn't enough material out there. The solar nebula, the disk of gas and dust from which planets formed, was too thin and spread out at those distances. Planet formation requires material to collide and stick together, and that process becomes exponentially slower when particles are spread across vast expanses of space. But if Planet 9 formed closer to the Sun, in the region where Uranus and Neptune formed, and was then ejected outward, suddenly its existence makes perfect sense. The physical characteristics match this origin story remarkably well. Planet 9 is predicted to have a mass of about 5 Earth masses, similar to Uranus and Neptune when you account for their thick atmospheres. It would be gaseous, an ice giant with a rocky core surrounded by water, methane, and ammonia ices, all wrapped in a hydrogen and helium envelope. These are exactly the characteristics you'd expect from a planet that formed in the outer solar system 6 billion years ago. But there's another possibility, one that's even more extraordinary. What if Planet 9 didn't form in our solar system at all? The Sun wasn't born in isolation. It formed in a stellar nursery, a dense cluster containing thousands of young stars packed into a relatively small volume of space. In such environments, close encounters between stars are common. During the first few 100 million years of the solar system's existence, another star could have passed within a few hundred astronomical units of the Sun. If that star had its own planetary system, and if one of its planets happened to be in just the right position during the encounter, the Sun's gravity could have captured it. This capture scenario would make Planet 9 an exoplanet, a planet that formed around another star. If confirmed, it would be the first exoplanet discovered within our own solar system, a world that spent billions of years orbiting a different sun before becoming part of ours. The odds of such a capture are low, but they're not zero. Computer simulations show that in dense stellar nurseries, planetary capture events do occur, though rarely. The capture hypothesis has an appealing elegance. It would explain why Planet 9's orbit is so different from the other planets, tilted relative to the solar system's plane and highly elongated. A captured planet wouldn't follow the orderly, nearly circular orbits of planets that formed in place. Its orbit would bear the fingerprints of a violent gravitational encounter, exactly what we see predicted for Planet 9. But here's what makes this puzzle even more complex. There's a third option that astronomers are seriously considering. What if there isn't just one Planet 9, but multiple smaller planets? What if instead of a single 5 Earth mass world, there are 2 or 3 planets, each a few Earth masses, scattered across the outer solar system? This multi-planet scenario could produce similar gravitational effects on trans-Neptunian objects while being harder to detect because each individual planet would be smaller and dimmer. Some researchers have proposed an even more exotic alternative involving a disk of small icy bodies with a combined mass of 10 Earth masses, spread across the outer solar system. This disk, if it exists, could gravitationally shepherd trans-Neptunian objects in ways that mimic the effects of a single large planet. The challenge with this disk hypothesis is that such a structure should be detectable through its infrared emission, and so far, surveys haven't found it. Then there are the truly speculative ideas. Could Planet 9 be a primordial black hole, a microscopic black hole formed in the early universe? Such an object would have the right mass to produce the observed gravitational effects but would be nearly impossible to detect directly. Or could it be a concentration of dark matter, the mysterious substance that makes up most of the universe's mass but doesn't interact with light? These exotic explanations remain on the fringes of scientific consideration because they require invoking phenomena we've never directly observed in our solar system. Occam's razor suggests the simpler explanation, a planet, is more likely. But the fact that astronomers are even considering such alternatives demonstrates how profoundly puzzling this situation is. What makes the formation question so crucial is this: the answer would tell us whether our solar system is typical or unusual. If Planet 9 is an ejected fifth giant, it suggests that planetary systems commonly lose planets during their chaotic youth. Astronomers have found evidence of ejected planets around other stars, so this wouldn't be unprecedented. It would mean that for every planetary system we observe, there might be one or more invisible planets lurking in the darkness beyond what we can easily detect. If Planet 9 is a captured exoplanet, it would suggest that stellar nurseries are dynamic enough to exchange planets between forming systems. This would have profound implications for understanding planetary demographics in the galaxy. How many stars captured planets? How many lost them? The architecture of planetary systems might be far more fluid and dynamic than we've imagined. Recent refinements to the Planet 9 hypothesis have actually made the formation question more pressing. A 2025 study using an expanded sample of 51 extreme trans-Neptunian objects proposed that Planet 9's orbit might be smaller than previously thought, with a semi-major axis of around 290 astronomical units rather than 400 to 600. If true, this would place Planet 9 closer to the Sun, making it brighter and easier to find, but it also changes the dynamical requirements for how the planet reached that orbit. The nice model simulations that showed a fifth giant being ejected to Planet 9's orbit were based on the earlier, larger orbital estimates. With a smaller orbit, the ejection dynamics would need to be recalculated. Could Jupiter fling a planet to 290 astronomical units without ejecting it entirely from the solar system? The answer depends on precise details of the ejection event, the angle, the velocity, the gravitational assists from other planets. What we're witnessing is science in action, the process of refining hypotheses as new data emerges. Each new trans-Neptunian object discovered adds another constraint to the models. Each failed search narrows the possible locations. The picture is becoming clearer, but the fundamental mystery remains. Somewhere out there, moving slowly through the darkness, there might be a world that holds the key to understanding our solar system's violent past. And the clock is ticking. Within the next few years, the Vera Rubin Observatory will either find Planet 9 or rule out large portions of the remaining search space. We're approaching a definitive answer to one of astronomy's biggest questions. But before we get there, we need to understand what finding Planet 9 would actually mean for the rest of the solar system, because its gravitational influence extends far beyond just those handful of trans-Neptunian objects. Planet 9's gravitational reach doesn't stop at those extreme trans-Neptunian objects. It extends throughout the outer solar system in ways that are subtle but detectable. Jupiter family comets, those periodic visitors that swing through the inner solar system every few years, would show different orbital tilts if Planet 9 exists. Computer simulations predict their inclination distribution should be broader, more spread out, than what we'd see in a Planet 9-free solar system. And when astronomers look at the actual data, that's exactly what they find. The distribution matches the prediction. Then there's the Oort cloud, that vast spherical shell of icy bodies surrounding the solar system at distances up to 100,000 astronomical units. Planet 9 would have affected how many objects got captured into the Oort cloud during the solar system's formation. Simulations show that with Planet 9 in its predicted orbit billions of years ago, fewer objects would have been flung into the Oort cloud. The gravitational stirring from a massive planet in the outer reaches would have ejected more objects entirely from the solar system rather than parking them in distant orbits. This prediction is harder to test directly since we can't count Oort cloud objects with any precision, but it represents another testable consequence of the hypothesis. What about the giant planets themselves? Would Planet 9 have left fingerprints on Jupiter, Saturn, Uranus, and Neptune? The answer depends on when Planet 9 reached its current orbit. If it was ejected early in the solar system's history, during the period of planetary migration described by the NICE model, then its ejection would have been part of the same chaotic reshuffling that moved all the giant planets. In that case, Planet 9's influence is already baked into the current orbital configuration we observe. The planets are where they are partly because of the gravitational chaos that sent Planet 9 outward. But there's a more direct effect. Planet 9's orbit is tilted about 6 degrees relative to the plane where the 8 known planets orbit. That tilt would exert a slow, subtle torque on the entire solar system over billions of years. Think of it like a spinning top that's slightly off balance. Over time, that imbalance affects the whole system's orientation in space. Calculations suggest that Planet 9 could explain a long-standing puzzle, why the Sun's equator is tilted about 6 degrees relative to the planetary orbital plane. The gravitational influence of a distant, tilted Planet 9, acting over 4.5 billion years, could have gradually torqued the entire inner solar system, including the Sun's rotation axis, into its current configuration. This prediction caught many astronomers by surprise when it was first published. It's one thing to affect distant icy bodies. It's another to tilt the Sun itself. But the math checks out. A 5 Earth-mass planet at 300 to 400 astronomical units, tilted at the right angle, applying gentle but persistent gravitational torque over geological timescales, could absolutely accomplish this feat. And suddenly Planet 9 isn't just explaining weird orbits at the edge of the solar system. It's explaining a fundamental property of our planetary system that's been visible since humans first pointed telescopes at the Sun. Yet another population shows Planet 9's fingerprints, high-inclination trans-Neptunian objects. These are objects whose orbits are tilted steeply relative to the plane where planets orbit, sometimes by 90 degrees or more. They're rare, which makes sense. Most of the solar system's material started in a flat disk and should stay relatively flat. But we found several objects with these extreme tilts, and they need an explanation. Planet 9's gravitational influence could pump up the inclinations of certain objects over millions of years through a process called correlative oscillations. This mechanism causes orbits to trade eccentricity for inclination in a periodic cycle. An object might start with a moderately elliptical orbit in the plane, then gradually become more circular but more tilted, then swing back. With Planet 9's gravity driving these oscillations, some objects could get kicked into very high inclinations and stay there. 5 known objects fit this prediction with remarkable precision. They're positioned at roughly 90-degree angles to Planet 9's predicted location, and their orbits are perpendicular to the solar system's plane. When Badigian and Brown first ran their simulations, these objects appeared naturally in the results. The model predicted they should exist before anyone had specifically looked for them. Finding them in the real data wasn't just confirmation. It was the kind of successful prediction that makes scientists take notice. The gravitational mechanisms at work here operate on timescales that dwarf human civilization. An object in the outer solar system might take hundreds of thousands of years to complete one oscillation cycle. Planet 9 itself takes 10,000 to 20,000 years just to complete a single orbit. The gravitational dance between Planet 9 and these distant objects unfolds across geological epochs, invisible to any observer watching for less than millennia. We're catching a single frame of a movie that's been playing for billions of years. Does Planet 9 affect the known planets directly? Neptune's orbit should show tiny perturbations if Planet 9 exists, wobbles measurable in the planet's position over time. Astronomers have looked for these signatures. So far, the results are inconclusive, which actually makes sense given Planet 9's distance. At 300 to 600 astronomical units, its gravitational pull on Neptune is extraordinarily weak. Neptune is 30 astronomical units from the Sun. Planet 9 is 10 to 20 times farther out. Gravitational force drops off with the square of distance, so Planet 9's pull on Neptune is hundreds of times weaker than Neptune's pull on itself. Detecting such subtle effects requires decades of precise observations and sophisticated data analysis. We might not see clear perturbations in Neptune's orbit for years yet. Uranus presents a different puzzle. This ice giant is tilted on its side, rotating with its axis nearly in the plane of its orbit rather than roughly perpendicular like every other planet. Various theories have tried to explain this bizarre orientation: a giant collision during formation, gravitational interactions during planetary migration, or cumulative effects from multiple smaller impacts. Could Planet 9 be responsible? Probably not directly. The tilt likely originated during the solar system's chaotic youth, and Planet 9's current location doesn't provide the right geometry to have caused it. But if Planet 9 was ejected from the inner solar system, it might have been one of several factors contributing to the orbital chaos that tilted Uranus. Not the sole cause, but part of a complex sequence of gravitational interactions. The asteroid belt between Mars and Jupiter seems far removed from Planet 9's domain, but even here there might be subtle connections. Some asteroids have been found on highly elliptical orbits that take them far beyond Neptune. These aren't main belt asteroids in the traditional sense, they're trans-Neptunian objects that happen to pass through the inner solar system. Planet 9 could influence the population of these objects, determining which ones get perturbed onto planet-crossing orbits and which stay safely beyond Neptune. This matters for understanding impact rates on the inner planets over geological time. If Planet 9 exists, it's been shaping the flux of impactors throughout solar system history. Centaurs, those hybrid objects orbiting between Jupiter and Neptune, neither quite asteroids nor comets, show dynamical properties that could reflect Planet 9's influence. These objects are thought to originate from the trans-Neptunian region and get gravitationally scattered inward. The rate at which objects get scattered, and the specific orbits they end up on, depend on the outer solar system's gravitational environment. Add Planet 9 to the mix, and you change the probabilities. More objects might get kicked onto certain types of orbits, fewer onto others. Detailed population studies of centaurs could, in principle, reveal Planet 9's gravitational fingerprint even in the middle reaches of the solar system. What's remarkable about all these effects is their consistency. Planet 9 isn't just explaining one weird thing. It's explaining multiple independent phenomena across different populations of objects in different regions of the solar system. The clustering of extreme trans-Neptunian objects. The perpendicular objects. The Sun's axial tilt. The distribution of orbital inclinations. Each one could potentially have a different explanation. But they all point to the same solution, a massive planet on a distant, tilted orbit. That's what makes the hypothesis so compelling. Still, correlation isn't causation. Maybe these effects have other explanations we haven't considered. Maybe observational biases we haven't properly accounted for are creating patterns where none exist. Maybe the solar system is just weird in multiple unrelated ways. These possibilities keep skeptics skeptical, and rightfully so. Extraordinary claims require extraordinary evidence. But with each new study, with each additional prediction that proves correct, the case grows stronger. The question isn't really whether Planet 9 affects the solar system. If it exists at all, it must. Gravity doesn't have an off switch. The question is whether we can measure those effects precisely enough to confirm the planet's existence indirectly. And that's where the cutting edge of observational astronomy comes in, techniques for detecting planets not by seeing them directly, but by mapping their gravitational influence on everything around them. The art of finding invisible planets has evolved dramatically since Neptune's mathematical discovery in 1846. Back then, astronomers noticed Uranus wasn't following its predicted path. Something was tugging on it. They worked backward from those perturbations, calculated where the disturbing mass had to be, pointed their telescopes at that spot, and there it was. A new world revealed through pure mathematics. Planet 9 requires a more sophisticated approach. We're not tracking one object getting pulled by an unknown planet. We're analyzing dozens of distant bodies, each with its own orbital peculiarities, trying to extract a common signal from the noise. It's less like following footprints to find what made them and more like being a detective at a crime scene with multiple witnesses who each saw something slightly different. The statistical methods matter enormously here. Brown and Badijan didn't just notice the clustering and declare victory. They quantified it. They developed techniques to measure observational bias in each individual object's discovery, because not all parts of the sky get observed equally. Some regions get scanned more frequently. Some get deeper exposures. Telescopes point where astronomers tell them to point, and astronomers have their own interests and observing programs. This creates selection effects. If you only search for distant objects in certain parts of the sky, you'll only find distant objects in those parts of the sky. Obvious, right? But correcting for this bias mathematically isn't straightforward. You need to know not just where you looked, but how thoroughly you looked there, and with what sensitivity. Brown and Badijan accounted for these factors, and even after corrections, the clustering remained statistically significant. About 1 chance in 500 that it's random. That number has gotten better with time. As more objects get discovered and the sample size grows, the statistical confidence strengthens. By 2021, Brown and Badijan reanalyzed with improved bias corrections and found a clustering significant at 99.6% confidence. That's getting into the realm where you start taking things very seriously. But statistics alone don't make a planet. The real power comes from prediction. If your hypothesis is correct, it should tell you what else you'll find. Planet 9 makes specific predictions about populations of objects that should exist but hadn't been looked for yet. And that's where things get interesting. One prediction involves objects perpendicular to the solar system's plane. Not just tilted. Perpendicular. Orbiting the sun almost vertically while everything else goes around horizontally. These objects shouldn't exist in a normal solar system. There's no mechanism to put them there. Yet Planet 9's gravitational influence, according to the models, should create exactly this population. 5 objects matching this prediction have been found. 5 might not sound like many, but remember, these are extremely rare configurations. Finding even one was surprising. Finding 5 that matched the theoretical prediction in detail. That's not coincidence. Another test came in 2024. Brown and Badigian published analysis of a different population, low-inclination trans-Neptunian objects with orbits that reach inside Neptune's orbit. These objects have nothing to do with the original clustering that suggested Planet 9. They're on completely different types of orbits. Yet when you run simulations with Planet 9 included, these objects' orbital distribution matches what we actually observe. Remove Planet 9 from the simulations, and the match disappears. The statistical rejection of the Planet 9 free scenario sits at 5 sigma. That's the same confidence level physicists demanded before announcing the Higgs boson discovery. Does this prove Planet 9 exists? No. Science doesn't deal in proof, only in evidence and confidence levels. But the confidence is getting high enough that dismissing the hypothesis requires explaining away multiple independent lines of evidence. The skeptics haven't been silent. Samantha Lawler and others argue that observational biases are stronger than Brown and Badigian acknowledge. In 2020, 2 large surveys, the Outer Solar System Origins Survey and the Dark Energy Survey, found hundreds of trans-Neptunian objects and saw no significant clustering. OSOS documented over 800 objects. DES found 316 new ones. Both surveys carefully accounted for observational bias and concluded the orbits could be explained by known physical processes without invoking a 9th planet. This disagreement cuts to the heart of how science works. Same solar system, same objects, different conclusions. Why? It comes down to which objects you include in your analysis and how you correct for bias. Brown and Badigian focus on the most extreme objects, the ones farthest out with the most elongated orbits. These are the objects most likely to be influenced by Planet 9 because they venture into its gravitational domain. OSOS and DES looked at a broader population including objects that wouldn't be strongly affected by Planet 9 even if it exists. The debate also involves sample size versus sample quality. OSOS has more objects, but are they the right objects for testing this particular hypothesis? 1,000 data points don't help if they're measuring the wrong thing. Meanwhile, Brown and Badigian's smaller sample focuses on exactly the objects that should show Planet 9's influence most clearly. It's a classic tension in observational astronomy. More data isn't always better data if it dilutes your signal. Alternative explanations have emerged. Maybe instead of one big planet, there's a disk of smaller icy bodies with combined mass equivalent to Planet 9. Spread that mass out, and you might get similar gravitational effects. Or perhaps these orbits were set during the solar system's birth, when the Sun formed in a stellar cluster and neighboring stars perturbed the outer reaches. Some researchers even propose multiple Earth-mass rogue planets rather than one super-Earth. Each alternative has problems. The disk hypothesis requires an improbably specific mass distribution that stays stable over billions of years. The stellar cluster scenario works for setting initial conditions but doesn't explain why the clustering persists today, billions of years after the Sun left its birth cluster. Multiple rogues would need to have been captured with just the right orbits and masses to produce the observed effects without disrupting everything else. What makes Planet 9 compelling isn't that it's the only possible explanation. It's that it's the simplest explanation that accounts for multiple independent observations. One object, one orbit, multiple predictions that keep being confirmed. That's powerful. The thermal emission angle offers another avenue. Planet 9, if it exists, is still cooling from its formation. At 5 Earth masses, it retains significant internal heat. Even at 47 Kelvin, frigidly cold by any human standard, it radiates in the infrared. This radiation should be detectable with the right instruments, particularly submillimeter telescopes that specialize in this wavelength range. The challenge is sensitivity. Planet 9's thermal signature is faint, and the infrared sky is crowded. Lots of things emit at these wavelengths. You need long integration times, careful subtraction of foreground and background sources, and the patience to search a large area of sky. Several groups are working on this, using facilities like the Atacama Large Millimeter Array. No detections yet, but the search continues. Direct optical detection faces a different set of challenges. At aphelion, Planet 9 could be 800 astronomical units away or more, moving through the most distant parts of its orbit. At that distance, reflected sunlight is vanishingly faint. You need large telescopes with wide fields of view, and you need to image the same regions repeatedly to detect motion. The Subaru telescope in Hawaii has been conducting systematic searches. So have other facilities. They've covered about 78% of the possible sky positions where Planet 9 might be. That sounds good until you realize the remaining 22% is still a huge search space. Statistically, Planet 9 is more likely to be near aphelion than perihelion, simply because it moves slower out there and spends more time in that part of its orbit. That's where Kepler's second law bites you. Objects sweep out equal areas in equal times, which means they crawl along when far from the Sun. If Planet 9 is currently near aphelion, it's at its faintest and hardest to detect. Bad luck for us, but that's the reality. The search isn't hopeless. It's methodical, systematic, and ongoing. Every survey that comes up empty eliminates possibilities and narrows the remaining search space. Brown and Badigian have refined their predictions multiple times based on new data, updating the most likely orbital parameters. Their current best estimate puts the semi-major axis around 380 to 460 astronomical units, though a 2025 study by Siraj, Chaiba, and Tremaine suggests it might be closer, around 290 astronomical units. Closer means brighter. Brighter means easier to find. And then there's the Vera Rubin Observatory, scheduled to begin operations in 2025, which changes everything. The Vera Rubin Observatory is unlike anything that's come before. Sitting on Cerro Pachón in Chile at 2,700 meters elevation, it houses an 8.4-meter primary mirror and the largest digital camera ever built for astronomy. 3 gigapixels. That's not a typo. The camera weighs 3 tons and captures an area of sky equivalent to 40 full moons in a single image. Why does this matter for Planet 9? 2 reasons. Coverage and cadence. Rubin will survey the entire visible southern sky every few nights. Not targeted observations of specific regions. The whole sky, repeatedly, for 10 years. Every object in that survey gets tracked automatically. The system compares new images to previous ones, flagging anything that moves, changes brightness, or appears where nothing was before. Planet 9, if it exists, moves. Slowly. Over months and years, it would shift position relative to background stars. That's its signature. Rubin's repeated imaging strategy is custom-built to catch exactly that kind of motion. You don't need to know where to look ahead of time. You just watch everything and let the data tell you what moved. Mike Brown's enthusiasm about Rubin isn't exaggeration. He spent years searching with Subaru, which is an excellent telescope but requires choosing where to point. Rubin doesn't. It watches. constantly, systematically. If Planet 9 is anywhere in the southern sky at a detectable brightness, Rubin will find it. Not might find it. Will find it. Scott Shepard estimates the probability at 70 to 80%, assuming Planet 9 exists and has the predicted properties. Those are good odds in astronomy. Mario Jurek points out that Rubin will increase the known population of trans-Neptunian objects from around 4,000 to potentially 40,000. That's not just more objects. That's better statistics, tighter constraints, and a far clearer picture of what's actually happening in the outer solar system. The timeline is aggressive. Megan Schwamm says the first year or two of Rubin operations should answer the question. Either Planet 9 shows up in the data, or the lack of detection tells us something definitive about where it isn't and what it can't be. This is the moment. After nearly a decade of predictions, simulations, and targeted searches, we're about to conduct the most comprehensive survey of the outer solar system ever attempted. If Planet 9 is real, 2025 through 2027 could be the years we finally see it. But what if Rubin doesn't find it? That's the scenario nobody talks about much, but it's worth considering. Absence of evidence isn't evidence of absence, except when you've looked everywhere the thing could possibly be. Rubin gets us close to that threshold. If Rubin completes its survey without detecting Planet 9, the hypothesis doesn't collapse entirely, but it gets significantly harder to maintain. Maybe Planet 9 is fainter than expected. Maybe it's in a part of the sky Rubin can't see as well. Maybe it's currently too close to the galactic plane where background star density makes detection difficult. There are outs. But they start sounding like special pleading after a while. The other possibility is that Planet 9 exists but isn't where the models predict. Orbital parameters have shifted multiple times as new data comes in. The 2025 Siraj study suggested a closer, less eccentric orbit than previous estimates. If that's correct, Planet 9 might be brighter and easier to find. But if the models are still off, we might be looking in the wrong regions entirely. Then there's the alternative explanations. What if the orbital clustering of trans-Neptunian objects isn't caused by a single planet but by a disk of smaller objects, each too faint to detect individually but collectively massive enough to produce gravitational effects? That hypothesis has been proposed. It works mathematically for some observations but struggles to explain others, particularly the perpendicular objects. Or what if the clustering is a transient phenomenon caused by something that's no longer there? A passing star could have perturbed orbits temporarily. The Sun's birth cluster could have left a dynamical imprint that's still visible today. Multiple captured rogue planets might produce similar effects without requiring a single massive world. These scenarios feel more contrived than a single planet, but they're not impossible. Brown has argued that rejecting Planet 9 means accepting 5 or 6 separate unexplained phenomena, each requiring its own cause. That's inelegant. Science favors parsimony. One explanation that accounts for multiple observations beats several disconnected explanations. But parsimony isn't proof. Sometimes reality is messy and complicated. The discovery of Ammonite, a new sednoid announced by the Subaru team, adds another wrinkle. Ammonite's orbit doesn't cluster with the other sednoids the way Planet 9's gravitational influence would predict. It's off on its own. That might mean Planet 9's orbit needs further adjustment to account for Ammonite. Or it might mean something else entirely is going on. Every new discovery refines the picture, but it also introduces new constraints that any hypothesis has to satisfy. That's how science works. You don't get to cherry-pick the observations that support your model and ignore the rest. You have to explain all of it. Brown and Badigian have been transparent about this process. They've updated their predictions multiple times based on new data. They've addressed criticisms. They've acknowledged uncertainties. That's not weakness. That's how you build a robust scientific case. You test it against everything, adjust when necessary, and see if it still holds up. The April 2024 paper on low-inclination trans-Neptunian objects is a good example. These are objects that cross Neptune's orbit, a completely different population from the extreme distant objects that sparked the original hypothesis. Yet when you model their distribution, Planet 9's gravitational influence predicts their observed spread with remarkable accuracy. No Planet 9. The distribution doesn't match. With Planet 9, it does. That's independent confirmation using a different dataset. Statistical confidence levels matter here. A 5 sigma result means the probability of the observation occurring by chance is less than 1 in 3. 5 million. That's the standard for discovery in particle physics. It's extremely stringent. The 2024 study rejected the no Planet 9 scenario at approximately 5 sigma confidence. That's not suggestive. That's strong. Brown's statement that he thinks it's very unlikely Planet 9 doesn't exist reflects this accumulating evidence. It's not arrogance. It's Bayesian updating. Start with a hypothesis. Test it against observations. Adjust your confidence based on how well it performs. After 8 years of testing, the hypothesis keeps working. That shifts the probability upward. Could everyone be wrong? Of course. Science has a long history of confident predictions that turned out to be false. Vulcan, the hypothetical planet inside Mercury's orbit, was predicted to explain perturbations that Einstein's general relativity later explained without needing an extra planet. The luminiferous ether seemed necessary until it wasn't. Confidence doesn't equal certainty. But here's the key difference. Vulcan was never observed. Planet 9 hasn't been observed either, but the effects attributed to it keep showing up in independent datasets. The orbital clustering persists after correcting for observational bias. The perpendicular objects exist. The low-inclination objects match predictions. The Jupiter family comet distribution changes in the expected way. The predicted reduction in Oort cloud capture efficiency aligns with simulations. That's a lot of things to get right by accident. It's not impossible, but it's increasingly unlikely. Each successful prediction raises the prior probability that the underlying model is correct. So where does that leave us as Rubin prepares to begin operations? We're at a decision point. Within 2 years, maybe 3, we'll have data comprehensive enough to either confirm Planet 9's existence or rule it out across most of its possible parameter space. This isn't the kind of question that lingers unresolved for decades. The technology exists. The survey is happening. The answer is coming. If Rubin finds Planet 9, it will be one of the most significant planetary discoveries in history. Not because it's a planet, though that's cool. Because of what it tells us about solar system formation, migration dynamics, and the possibility that our planetary census was incomplete for the entire history of astronomy. If Rubin doesn't find it, that's also significant. It means either the hypothesis was wrong, or Planet 9 is so far, so faint, or so weirdly positioned that even our best efforts can't detect it. That possibility can't be dismissed. The outer solar system is vast. Assumptions about brightness and location might be off. But at some point, a hypothesis that can't be tested stops being useful. The broader implications extend beyond our solar system. Discovering Planet 9 would make our system more similar to others. Most exoplanetary systems contain super-Earths, planets with masses between Earth and Neptune. We don't have any. Planet 9 would fill that gap, suggesting that our system formed similarly to others, but with a quirk: one of the planets got kicked outward instead of staying close. That has implications for planet formation theory. How common is ejection? What determines whether a forming planetary system ends up with all its planets in tight orbits versus having one or more in distant eccentric orbits? Are we typical or unusual? Planet 9 helps answer those questions. It also affects how we think about planetary migration. The NICE model explains a lot about how the giant planets reach their current orbits, but it's not complete. If Planet 9 is an ejected ice giant, that's a direct observation of a process we've only simulated. We could study its composition, atmosphere, and thermal properties. We could learn what happens to a planet that gets thrown into the outer darkness and survives there for billions of years. All of that depends on detection. And detection depends on Rubin. The next few years will be decisive. The search itself has an interesting dynamic. Brown and his team aren't the only ones looking. Multiple groups worldwide are scanning different portions of the sky, using different methods, hoping to be the first to spot it. There's a competitive element, though it's mostly friendly. Everyone wants the discovery, but everyone also wants the answer, regardless of who provides it. What happens if Rubin spots something in the right region with the right motion? Confirmation would take time. A single detection isn't enough. You need multiple observations over weeks or months to establish an orbit. Then you need spectroscopy to determine composition. Is it icy? Gaseous? Does it have an atmosphere? What's its temperature? All of that requires follow-up with other instruments. And here's something people don't always consider. If Planet 9 exists and Rubin finds it, that's not the end of the story. It's the beginning. We'd have a new planet to study. A super-Earth in our own solar system, close enough to observe in detail but far enough to be genuinely alien. What can we learn from it? For one thing, we could study its atmosphere if it has one. Most super-Earths we've detected around other stars are too far away for detailed atmospheric analysis. Planet 9 would be right here, relatively speaking.